In this presentation, we talk about what happens when light encounters a medium and travels through that medium, and that's when refraction occurs. So refraction is basically the bending of light, and it doesn't have to be light. So basically any wave, but I'm going to just refer to this as light because we're talking about light. But it is the bending of a wave as it enters a medium and travels through that medium. So basically what happens, and we're going to focus on light, is that light slows down when it enters matter. We talked a little bit about how electromagnetic waves slow down when they enter matter because the light actually interacts with the matter and the charges that make up the matter. Because of the fact that the speed changes, the light wave actually bends. And the amount that the light bends depends on how much the light slows down when it enters the medium. If it has a very large change in speed, it's going to bend more than if the speed just changes a little. So I want to remind everyone at this point that when light travels in a vacuum or in air, it travels at the speed of light, that constant value c, which is 3 times 10 to the 8 meters per second. And so what happens is that when it enters a medium, like in this particular case here, I have light that's traveling in air, and then it enters water, and we can see that the light actually tends to bend. We have a normal to the surface right here, so that's perpendicular to the water's surface. We have an angle of incidence, and then we have the light entering that medium, and it tends to bend. And the reason that it's bending is because the light is slowing down. When the light slows down, the frequency of the light stays the same. We talked about this earlier, but the wavelength changes, it decreases. And so we can see that here is a picture of the wave fronts. So each one of these lines represents one wavelength in air, and as the light enters the medium, those wavelengths get smaller, but the frequency stays the same. We used this analogy before, but I'm going to mention it again. This analogy of a cart moving from a sidewalk into a grass. So here's a picture of the cart that's moving on a sidewalk, which is very smooth, very easy for those wheels to turn. And then when it hits the point where it meets the medium, the grass medium, and the grass, of course, imagine it's very thick glass, right? So the cart is going to want to slow down when it enters the grass. Because the first wheel here on the left hits the grass first, it slows down first, and the other wheel continues to travel at a faster speed, and that causes this shift in the cart. But once that other wheel enters the grass completely, then they travel at the same speed again, and then they travel along that straight line path. But there was a bend because of the fact that essentially one wheel was traveling slower, the other one was traveling faster, and it caused this curve or this bend in the path. It's just an analogy to think through why this is happening. So we could ask, how much does the speed of light decrease when it enters a medium? And it turns out that it depends on the type of the medium and how the light interacts with the medium itself. So when light enters a piece of glass, it's going to slow down differently than when it enters water versus maybe when it enters diamond. A measure of how the speed of light changes when it enters a medium is something called the index of refraction. And so all materials have where I have to be careful. So all materials where light can enter have a particular index of refraction associated with them. And the index of refraction is defined as the ratio of the speed of light in a vacuum, that's our C value here, which is a constant, that's our 3 times 10 to the 8 meters per second, divided by the speed of light in the material, or the medium. The speed of light in the medium, it's slower than the speed of light in the vacuum, and so this ratio, the value for C, is always going to be greater than the value for the speed of light inside the medium, and that means that this fraction is always going to be greater than 1. So the index of refraction is something that will be defined or can be calculated for different materials. So as I mentioned, that value for the index of refraction should always be greater than or equal to 1. It will be equal to 1 if we're in air, or in a vacuum, because then the speed, v, would be the same as the speed of light in the vacuum, and that ratio would be 1. If you get a number for an index of refraction that's less than 1, then you've done something wrong. That index of refraction is an indicator of how much the speed of light in the medium differs from that of the speed of light in the vacuum. So the closer that the index of refraction is to 1, the closer the speed of light is in that material to what it would be in a vacuum. The bigger the index of refraction is, the further away it is from the speed of light in air or in a vacuum, and the slower that the light is traveling. So a larger index of refraction implies a slower speed of light in the material. I guess I just said this right. So the bigger the index of refraction, the slower the speed of light is inside the medium. And we can rearrange this expression that we've defined the index of refraction. We can cross multiply here, and we see that the speed of light inside of a medium is just the speed of light in a vacuum. That's our 3 times 10 to the 8 meters per second, divided by the index of refraction of whatever that material is. So just to give us some ideas of what the speed of light is in different materials, we said that in a vacuum, of course, that's the vacuum of space. The speed of light travels at a particular speed. That's our constant value. That's 3 times 10 to the 8 meters per second. In our atmosphere, it's slightly less than the speed of light in a vacuum, but we always round it off. So essentially in air, we say that light travels at 3 times 10 to the 8 meters per second. Water has an index of refraction of about 1.33. So if I calculate the speed of light in water, it would be the speed of light in a vacuum, 3 times 10 to the 8 meters per second, divided by the index of refraction, which is 1.33, and I get 2.26 times 10 to the 8 meters per second. So 10 to the 8 is pretty big, right? Still traveling really fast. If I calculate what the speed of light is in glass, which has a larger index of refraction, I see that the speed of light would be the speed of light in a vacuum divided by the index of refraction, so it's 2 times 10 to the 8 meters per second. And then finally, if I look at diamond, I would take the speed of light in a vacuum, divide by 2.44, and I get 1.23 times 10 to the 8 meters per second. So as the index of refraction of the material increases, the speed of light decreases. So let's look more carefully at the law of reflection, and we're going to see exactly what's happening. I'm going to pull up the PhET simulation, which is a great simulation for this, and we're going to play with a little bit. We're going to see in the simulation that part of the incident ray is actually reflected. So here's a picture of the simulation where I have air at the top, water at the bottom, and I have my angle of incidence set at 60 degrees, and I can see that my angle of refraction is right around 40, and that the light reflects off here, and that reflection is at an angle of 60 degrees. So part of the ray is bent, that's this one that travels through the medium, and it is refracted. And that happens because, of course, the speed of light in water is less than the speed of light in air. So let's go ahead and take a look at that simulation. So here we go. Let's try it again. Okay, so the first thing I need to do is to bring up my protractor, and I need to set it up so that it is zeroed. There we go. Right, and so the crosshairs are essentially right on the 0 mark. I think it's zeroed. And then I have it set at air, and I have it set at water. So I can go ahead and I can click on this, and I'm going to go ahead and I'm going to move this to 60 degrees. And I can see that the angle of reflection is also 60 degrees. Remember that I measure everything with respect to the normal, which was that dotted line that's perpendicular to the surfaces that are meeting. And then I see that my angle of refraction, so angle of incidence is 60, angle of refraction is 40. So this is something I'm just going to show really quickly. The intensity of the light here that's coming in is 100%. What happens is that some of the light is reflected, and so in this particular case about 11% is reflected, and then the rest of it, around 89%, right, is refracted. So we still have all of the light that we started with. Some of it is reflected and some of the light is bent. Something that we're going to see on another slide, actually let's pull it up here, is this symmetry in refraction and the principle of reversibility. So when the light traveled from air into water, I had a 60-degree angle of incident and a 40-degree angle of refraction. And what can happen is that there's this principle of reversibility. So if I were to shine the light instead up through the water at 40 degrees, it would bend in air at 60 degrees. So let's give that a try. So here's the picture, and I turned it upside down because just to understand that we're now shining the light from the water and it's refracting into the air. And the reason it looks like that is because of the way this simulation works. So I can't, you'll notice I can move this around, right? But I can only move it 90 degrees. I can't pull it down below. So what I'm going to do is I'm going to put this at 40 degrees. I'm going to switch the top to water. And while we have it here, let's go ahead and say something about this. If both of the surfaces are the same, then the light just travels straight through, right? So here's 40 degrees, here's 40 degrees. There's no reflection because it's the same surface. Okay, so now I'm going to make this air down below. And so the light comes in. It's starting in water at 40 degrees. It hits that surface. Some of the light reflects off at 40 degrees, and some of it bends into the air, and this is about 60 degrees, right? So I guess it's just a matter of me getting it exactly right. And well, anyway, we get the idea that it's right around 60 degrees. So there's this principle of reversibility. So here I had 40 degrees in water and I get 60 degrees in air. And if I reverse this and I make this air and water and I put this at 60, I still have 60 degrees in air and 40 degrees in water. So it doesn't matter where the light starts. There's this principle of reversibility that you could actually switch where the light starts and where it was refracted, and they would still follow that same path. One of the things that you may have also noticed is that the larger angle, the incident angle or the refracted angle, is always in the region with the smaller index of refraction. So in this particular picture, this was our air, and our angle of incidence was 60 degrees, for example. And when the light entered the water, the angle was 40 degrees. And so where the light travels fastest, it has a smaller index of refraction. So up here is air, small index of refraction, larger angle, faster speed. Smaller index of refraction means it's traveling faster. When it enters the medium, the angle is smaller. This one was 40 degrees. The index of refraction was larger, and it's traveling slower. And that's always going to be the case. So the larger angle, whether it's the incident angle or the refracted angle, will always be in the region where the light is traveling the fastest and it has the smallest index of refraction. And we saw that even when we reversed this, right? So here is the larger angle in air, smaller angle down here in water. And if we reverse this and we make this air and we make this water, ooh, there's something going on there that we're going to talk about later. So there's my 40 degrees, and the angle down below is 60. So the larger angle is still associated with the smaller index of refraction and the faster speed. It's just something to kind of keep in mind when we look at refraction. So I just mentioned this, bigger angle difference. Oh, actually I didn't. So the bigger the difference between the indices of refraction in the regions, the more the light is going to bend. So when both of the substances were water, we saw that the light didn't bend at all. It just traveled straight through. So the bigger the difference is between those indices of refraction, the more the light's going to bend. And the closer the indices are together in terms of those two regions, the less the light is going to bend. So if light is incident from air into the following materials, in which case will light bend the most, and in which case will it bend the least, and let's check it out with a PhET simulation. All right, so let's come over here. Let's put this back to air. Let's put this first to water. All right, let's just put it at 50 degrees. So let's see what happens. I'm starting off with water, and I'm going to increase the indice of refraction right here. So I'm going to increase this value from water to glass, and we're going to see what happens to the bending of the light. So right now it's bending. Actually, let's start with it in air and air. It doesn't bend at all. When I put water in there, it bends, and let's watch what happens as I increase the index of refraction. As I increase the index of refraction, the light bends more and more, right? So now I have more bending. So when it's in water, it bends less than when it's in glass, and then there's different types of glass. Let's go all the way up to 1.6 if this simulation will do that. If I continue to go, the light continues to bend more and more. So the angle is less, but the bending itself is more. So in which material, if I start off in air, which material will the light bend the most? Well, air has an index of refraction of 1, and the biggest difference would be if I made this flint glass, right, which is 1.6. We could also ask, how could I layer these materials to get the least bending of light? And I would want to layer them so that they have the closest indices of refraction. And so I guess I would say that the ones that are the closest together would be crown glass and flint glass. That's a difference of 0.1. Over here, this is a difference of 0.17. So I would want to layer the flint glass and the crown glass to get the least bending of light. Let's give it a try. So let's make the top be regular glass and the bottom is flint glass. And let's put this angle at 40 degrees. And over here, you know, the angle is it's not quite 40. It's still some bending, right? So the angle down here is like maybe 37, but the light is not bending as much as if this top one were water, right? Can see that it's bending less. Let's put it here, right? Here's the water. The light is actually bending less when it's glass, right? It's almost traveling straight through. And of course, if they're made of exactly the same material, it goes straight through. So you get the least bending when those values are very close together.